The universe is vast, strange, and full of mysteries that challenge everything we think we know about reality. From dark flow, where entire clusters of galaxies are being pulled towards something unseen, to the eerie existence of rogue planets drifting through space without a star to orbit, the cosmos offers more questions than answers. Even the stars themselves defy our expectations, with some surviving thermonuclear explosions to become zombie stars, and others being hurled across the galaxy at unimaginable speeds as hypervelocity stars. Subscribe to the channel and join me as we explore these mysteries. The dark flow, where are they going? In the depths of space, far beyond the reach of our solar system, and even the galaxies we know, there's a mysterious phenomenon that has puzzled astronomers for years. It is known as dark flow. Picture enormous clusters of galaxies, each containing billions of stars, planets, and other cosmic bodies moving through space together. But what makes dark flow so unusual is that these clusters are speeding in one specific direction at velocities that defy our understanding of how the universe should behave. According to everything we know about the cosmos, galaxies are supposed to follow the expansion of the universe, which is happening uniformly in all directions. This means that galaxies should be moving away from each other as space itself stretches out. But dark flow suggests something different. These galaxy clusters are moving against the expected flow, as though being drawn towards something far beyond our current ability to see or understand. This movement is fast, and it's puzzlingly consistent. It's as if they are being pulled by an unseen force, a gravitational tug that lies in a region of space we cannot observe. What could be out there? One of the most intriguing ideas is that these galaxy clusters are being pulled towards something beyond the limits of the observable universe. The observable universe is the portion of the universe we can see with telescopes, limited by the speed of light. Beyond this boundary, there might be something so massive, so powerful, that it's dragging entire galaxies toward it. But we can't observe it directly, leaving us to wonder what could lie beyond the cosmic horizon. Some scientists speculate that what's pulling these galaxies could be an enormous structure, possibly a collection of matter so dense that it exerts a gravitational influence on a colossal scale. It's almost like a massive object hiding just out of sight, but its pull is strong enough to affect things millions of light years away. Others suggest that dark flow could be a sign of something even stranger, perhaps a link to another universe or another part of space-time that behaves differently from the part of the universe we know. This leads to mind-bending possibilities. What if, beyond the edge of our observable universe, there exists another universe entirely? Could the force drawing these galaxies be a kind of bridge between different realms of space-time? If so, it would imply that our universe is just one bubble in a larger cosmic sea, a multiverse where many other universes exist alongside our own. The idea that these clusters are being pulled toward a hidden realm and an unobservable part of existence opens up questions we can barely begin to answer. Could they be heading toward a region of space where the rules of physics are different from those we know? It's possible that dark flow could be evidence of a deeper structure to the cosmos, one that we've only begun to glimpse. Maybe there are forces or objects out there that don't behave in ways we can predict, or maybe these galaxies are on a journey towards something that exists outside the universe entirely, something we can't even imagine with our current understanding. What is pulling these galaxies, and why? If we imagine the universe as a giant tapestry with galaxies and stars woven into it, it's as if some invisible hand is tugging on one thread, pulling a part of the universe toward an unknown destination. The scale of this movement is staggering. These galaxy clusters are among the largest structures in the universe, and they are being shifted in a way that suggests a force or presence much larger and more powerful than anything we know of. Could this be a sign of an entirely different region of space-time, a realm where the laws of physics we're familiar with break down or take on a different form? The idea that these galaxies are being drawn towards something unknown, something that exists outside our view, is both fascinating and unnerving. It raises fundamental questions about the nature of the universe itself. Is there an edge to space? Or do these galaxies continue on a path that leads to something beyond, something that defies our understanding of existence? Some theories suggest that dark flow might hint at the existence of a hidden structure or mass that was left over from the early moments of the universe, something that formed in the first fractions of a second after the Big Bang. If true, it would mean that whatever is causing dark flow has been influencing the universe for nearly 14 billion years, a mysterious force that has been at work since the universe's infancy. But even then, this explanation doesn't tell us where these galaxies are going. It only suggests that they've been moving in this direction for an incredibly long time. What if dark flow points to something even more profound? Could it be that our understanding of the universe's expansion is incomplete, and that there are forces at play that we simply don't yet understand? If so, it would mean that our entire model of how the universe works, its structure, its growth, and its future, might need to be revised. The possibility that dark flow could point to an unseen part of the cosmos or to a force beyond our comprehension stirs the imagination. It beckons us to look deeper, to question everything we think we know, what we think we know about the universe. If these galaxies are indeed being drawn towards something beyond the observable universe, then we are faced with the tantalizing possibility that our universe is just one small part of a much larger, much stranger reality. Oumuamua, the interstellar visitor. In late 2017, something extraordinary happened. For the first time in recorded history, a visitor from outside our solar system passed through, leaving scientists with more questions than answers. The object, named Oumuamua, after a Hawaiian term meaning scout or messenger, was unlike anything we had ever seen before. Its elongated cigar-like shape, its unusual speed, and its trajectory all pointed to one thing. This was no ordinary space rock. Oumuamua came from somewhere far beyond the reach of our system. When Oumuamua was first detected, astronomers were puzzled. Initially, they thought it might be a comet, but it didn't have the familiar halo of gas and dust that comets typically develop when they pass close to the sun. Then they considered that it could be an asteroid, but its shape and behavior didn't match any known asteroid patterns. Oumuamua was long and thin, like a stretched-out cigar, and it was tumbling end over end as it traveled. No known natural object had ever been seen with such an unusual shape or motion. As Oumuamua continued its journey, it became clear that it was moving faster than expected. It didn't follow the usual paths of objects in our solar system, which typically orbit the sun or travel on more predictable trajectories. Instead, Oumuamua seemed to be speeding up as it moved away from the sun, defying the typical gravitational influence that should have slowed it down. This unexpected acceleration added yet another layer of mystery to an already perplexing object. One of the most striking features of Oumuamua is its origin. All evidence suggests that it didn't come from within our solar system. Instead, it appears to be an interstellar object, something that traveled across the vast distances of space from another star system before passing through ours. It's difficult to comprehend just how far Oumuamua must have traveled to get here. The nearest star system to our own, Alpha Centauri, is over 4 light-years away, an almost unimaginable distance. Wherever Oumuamua came from, it had likely been journeying through the cold, empty reaches of interstellar space for millions, if not billions, of years before it entered our solar system. But where did Oumuamua come from? What kind of object is it? These questions have led to a wide range of theories. Some scientists believe it could be a fragment of a larger planet or asteroid that was torn apart during a violent collision in another star system. Over time, the fragment could have been ejected from its home system and sent hurtling through interstellar space until it reached us. If this theory is correct, Oumuamua might be a remnant of a distant world, a piece of cosmic debris from a place we may never know. Another possibility is that Oumuamua is a type of comet, but one that lost most of its volatile materials, like ice and gas, during its long journey. If this were the case, Oumuamua might have started its life as a more typical comet. But after spending millions of years traveling through space, it could have lost the materials that would normally form a bright, glowing tail when it approached the sun. This could explain why Oumuamua didn't behave like the comets we're familiar with, yet still showed some signs of unexpected acceleration, which could be due to small amounts of gas escaping from beneath its surface. However, the odd shape, rapid spin, and unusual acceleration of Oumuamua have led some scientists to consider a far more intriguing possibility. Could it be an artificial object? Could Oumuamua, with its elongated shape and strange behavior, actually be an alien probe or spacecraft? This idea, while speculative, has captured the imagination of many. Oumuamua's acceleration, in particular, is hard to explain using known natural processes. Some scientists have suggested that if Oumuamua were an alien probe, it might be powered by some kind of propulsion system we don't yet understand. Its long, thin shape could be ideal for such a craft, especially if it were designed to minimize friction as it travels through space. Others have proposed that Oumuamua could be a type of light sail, a thin, lightweight structure pushed through space by radiation from stars. This idea isn't purely science fiction. Humans have already developed light sails for small spacecraft, and it's possible that an advanced alien civilization could have created a much larger, more sophisticated version. Of course, the idea that Oumuamua is an alien spacecraft or probe is highly controversial. Most scientists believe that natural explanations are far more likely, and they point to the lack of any direct evidence of artificial features on Oumuamua. But the fact remains that Oumuamua is unlike anything we've ever seen, and its strange characteristics continue to spark debate. Oumuamua's journey through our solar system was brief. It sped past the sun and continued on its way, leaving us with only a short window of time to observe it. As it moved farther from the sun, it became harder and harder to track, and eventually it disappeared from our view altogether. In the years since, scientists have continued to analyze the data collected during Oumuamua's brief visit, trying to unravel the mysteries it left behind. One of the most fascinating aspects of Oumuamua's visit is what it represents. It's a reminder that our solar system is not an isolated island in space. We are part of a much larger, interconnected universe filled with objects, forces, and phenomena that we are only just beginning to understand. The fact that Oumuamua came from another star system shows that interstellar travel, even for natural objects, is possible. It raises the possibility that other objects, like Oumuamua, have passed through our solar system before unnoticed, and that more will follow in the future. It also prompts us to wonder about the origins of such objects. If Oumuamua is just one of many interstellar travelers, what else might be out there, journeying through space from one star system to another? Could some of these objects carry clues about the formation of distant worlds? Could they even be remnants of civilizations that existed long before our own? The lopsided universe, cosmic imbalance. As we continue to explore the vastness of space, it becomes clear that the universe is far from being a perfectly ordered, balanced place. At first glance, it may seem like the cosmos is evenly spread out, with galaxies, stars, and planets scattered throughout. But the truth is more complicated. In reality, the universe is lopsided. There's an imbalance in the way matter is distributed across the cosmos, and this unevenness has sparked questions and debates among scientists. We've long believed that the universe, on a large scale, should be uniform. This idea comes from the assumption that the Big Bang, the event that started it all, would have created a universe where matter and energy are distributed fairly evenly. But as we look more closely, we see that this isn't the case. Instead, some areas of the universe contain more matter, while others have far less. This lopsidedness raises an important question. Why? What caused the universe to form in such an unbalanced way? One possible explanation is that something unusual happened in the earliest moments of the universe's existence, right after the Big Bang. The universe expanded rapidly in an event known as inflation. During this incredibly brief but intense period of growth, tiny fluctuations in the density of matter may have been magnified, leading to the uneven distribution we see today. If these fluctuations were small to begin with, they could have been amplified over billions of years, creating areas with a higher concentration of matter and others with much less. But while this theory explains part of the imbalance, it doesn't fully account for the scale of the lopsidedness we observe. It's as though something else is at work, something more mysterious than inflation alone. Some scientists believe that dark matter, the invisible substance that makes up a significant portion of the universe's mass, could be playing a role in this uneven distribution. Dark matter doesn't interact with light the way ordinary matter does, so we can't see it directly, but its gravitational effects are visible, pulling galaxies together and shaping the large-scale structure of the universe. Perhaps dark matter, in some way we don't yet understand, is contributing to the lopsided nature of the cosmos. Others suggest that this imbalance could be the result of forces or events that we haven't yet discovered. Maybe there's a fundamental aspect of the universe that causes it to prefer asymmetry over balance. If that's the case, it challenges our ideas about the nature of the cosmos. We like to think of the universe as a place where order and symmetry prevail. Yet as we study the universe more deeply, it seems that chaos, unpredictability, and imbalance are just as much a part of its design. This lopsidedness also raises a more philosophical question. Does the imbalance we see in the universe suggest that asymmetry is a fundamental part of existence? If the universe itself is uneven, does that mean that imbalance and chaos lie at the heart of everything, from the smallest particles to the largest galaxies? It's a curious idea. On Earth, we often think of symmetry as a marker of beauty and perfection. We find comfort in patterns and balance, whether it's in the natural world or in human-made objects. But when we look at the universe, we see that the largest structure we know, space itself, follows different rules. It's messy, unbalanced, and irregular. Yet, within this cosmic imbalance, there is still order. Galaxies form, stars are born, and planets, including our own, come into existence. It seems that asymmetry, rather than detracting from the universe's beauty, is what allows it to evolve and create the complexity we see today. If the universe were perfectly uniform, it's possible that none of the structures we know would have formed. There would be no galaxies, no stars, no planets, just a smooth, featureless expanse of space. Instead, the universe's unevenness has allowed for the clumping of matter, the formation of galaxies, and eventually the creation of life. So perhaps this lopsided nature isn't just a quirk of the universe, but a necessary condition for its existence. Without imbalance, there might not be a universe as we know it. But this still leaves us wondering, why is the universe this way? Could the uneven distribution of matter point to forces we don't yet understand? Some scientists have even suggested that this lopsidedness might be a clue to the universe's origins. If the cosmos started with some form of imbalance, it might explain why it evolved in the way that it did. But if that's true, what caused the initial imbalance? Did the universe have a chaotic beginning where randomness and asymmetry ruled? Or is there some deeper reason, some unknown force, that made the universe this way? One possible explanation is that the laws of physics themselves favor imbalance in certain processes. Symmetry breaks down naturally, leading to the creation of uneven structures. We see this on small scales too. For example, in the quantum world, particles often behave in unpredictable, asymmetrical ways. Maybe the same is true on the largest scales, with the universe's lopsided nature being a reflection of deeper, more fundamental principles. Another intriguing idea is that the universe's imbalance could be tied to the existence of other universes. If our universe is just one of many, perhaps the asymmetry we see is a result of interactions or influences from these other universes. Could the pull of another universe, or the gravitational effects of something beyond our cosmos, be contributing to the lopsided distribution of matter? This opens the door to even more questions about the nature of reality and whether our universe is truly isolated or connected to something far larger. No matter the cause, the fact remains that the universe is uneven, and this imbalance plays a key role in shaping everything we see. It's a reminder that chaos and unpredictability are essential parts of the cosmos. Far from being a perfectly ordered, symmetrical place, the universe thrives on irregularity and imperfection. In this sense, the lopsided universe challenges our understanding of order and disorder, suggesting that even the most massive structures in existence are shaped by forces that favor imbalance over symmetry, a universe of multiple realities. In the fabric of the universe, time does not behave in the way we might expect. What we experience as a steady, unchanging tick of a clock is actually deeply influenced by the forces and speeds around us. This concept, known as time dilation, shows us that time itself can slow down or speed up depending on where you are and how fast you're moving. It challenges our very understanding of what time is and raises fascinating questions about how the universe feels to beings in different parts of it. Time dilation occurs in two extreme situations: when an object is moving close to the speed of light, or when it is near an extremely strong gravitational field, like the one surrounding a black hole. In both of these cases, time slows down dramatically. For someone moving at near light speed or living near a black hole, seconds would stretch out, minutes would crawl, and hours could seem to take an eternity. This difference in the flow of time can seem like science fiction, but it's a real and measurable effect, one that has been proven by scientists here on Earth. GPS satellites, for example, which orbit high above the Earth, move fast enough that their clocks tick slightly faster than those on the ground. Without correcting for this time difference, GPS would quickly become inaccurate. But as extreme as this effect is in orbit, it's nothing compared to what happens near the edge of a black hole, a place where gravity is so intense that it warps not only space but also time. Imagine standing on the surface of a planet orbiting close to a black hole. The immense gravitational pull of the black hole would stretch and distort time for you. Time would pass almost normally, but if you looked out into space and saw a distant observer, perhaps someone on Earth, their experience of time would be completely different. While only a few hours might pass for you near the black hole, days, months, or even years could be passing for the observer far away from the strong gravitational field. The closer you get to the black hole, the more pronounced this effect becomes. If you were to hover just outside its event horizon, the point beyond which not even light can escape, time would slow down to such an extent that from your perspective, the universe outside would seem to speed up dramatically. Stars would appear to age and die. Galaxies would collide and merge, and the entire history of the cosmos could play out before your eyes, all while you barely aged at all. It's almost impossible to imagine how different the universe would feel to beings who live near such extreme gravitational fields. For them, the flow of time would be entirely different from what we experience on Earth. If we were ever to encounter such beings, they might perceive us as moving in fast forward, while we would see them as almost frozen in time. Could we ever communicate with them? Or would the differences in our perceptions of time be too great to overcome? This idea that time itself can vary across the universe challenges the very notion of what we think reality is. On Earth, we experience time as a constant, something that moves forward at a steady, predictable pace. But the universe doesn't follow that rule. Time is not a fixed construct, but something that bends and shifts depending on the forces at play. It's deeply tied to space, creating a dynamic fabric known as space-time, where what happens to one affects the other. For beings in different parts of the universe, reality itself could feel completely different depending on how time flows where they live. To someone near a black hole, the universe outside would seem to rush forward, almost too fast to comprehend. To us on Earth, their reality would seem painfully slow. Could there be entire civilizations living near black holes, experiencing time at a fraction of the speed we do, unaware that for us, ages have passed in the blink of an eye? Time dilation also raises fascinating questions about the possibility of meeting beings from other parts of the universe. If time flows differently for them than it does for us, what would such a meeting look like? Would we even be able to communicate with them, or would the differences in our experiences of time make meaningful interaction impossible? It's also worth considering how time dilation affects our understanding of travel across the universe. If we were to travel at near light speeds, time would slow down for us compared to someone staying on Earth. This means that while a journey to a distant star might take hundreds of years from the perspective of someone on Earth, it could feel like only a few years to the traveler. This effect, known as time dilation in special relativity, makes the dream of interstellar travel more conceivable, at least for the travelers themselves. But for those left behind, entire generations could pass before the travelers return, if they return at all. All of this forces us to ask, is time really the steady, unchanging thing we've always believed it to be, or is it a flexible, shifting phenomenon that varies depending on where you are in the universe? If time isn't constant, what does that say about the nature of reality itself? Could our perception of time be just one version of reality, one that feels normal to us but might be entirely alien to beings living elsewhere in the cosmos? In a universe where time flows differently depending on your location and speed, reality becomes a relative concept. For us, time seems linear. It moves from the past to the present and into the future, with each second lasting exactly the same amount of time. But for someone moving at near light speed, or someone living near a black hole, time would feel completely different. Does this mean that there are multiple versions of reality, each shaped by the flow of time in different parts of the universe? These questions don't have easy answers, but they challenge us to think about the universe in new ways. Time, it seems, is not the straightforward, unchanging thing we once thought it was. Instead, it's something far more complex, something that varies depending on where you are and how fast you're moving. This idea that reality itself could be shaped by the flow of time forces us to reconsider our understanding of the universe and our place within it. Rogue planets, worlds without suns. Among the stars of our galaxy, there are countless planets, many orbiting their suns just as the Earth orbits the sun. But not all planets have a home. Some drift through space, cold and alone, without a star to anchor them. These are rogue planets, worlds without suns, wandering through the darkness of the galaxy. Unlike the planets we are familiar with, which are bound by the gravitational pull of their stars, rogue planets float freely through space, untethered and isolated. What's more, it's estimated that there could be more rogue planets than stars in our galaxy. How these rogue planets came to be is still a matter of debate among scientists. There are a few different possibilities for how a planet might become a drifter, cut off from the light and warmth of a star. One of the leading theories is that rogue planets are the remnants of once thriving solar systems, planets that were formed around stars but later ejected by gravitational forces in the chaotic early stages of a solar system's life. As planets are forming and jockeying for position, some can be thrown out into space, cast adrift by the complex gravitational interactions between other planets and the star they once orbited. These planets are effectively exiled from their systems, left to drift through the galaxy. It's also possible that rogue planets might form in isolation without ever being part of a solar system. In the vast clouds of gas and dust that make up a galaxy, planets might form directly from collapsing material, much like stars do. These planets wouldn't have a star to orbit from the start, forming in the cold and dark of space rather than in the warm embrace of a solar system. This scenario suggests that some rogue planets might be truly solitary from the moment of their birth, never knowing the light of a sun. But what kind of environment would exist on a rogue planet, so far from the warmth and light of a star? The surface of such a planet would be unimaginably cold, with temperatures plummeting to extremes due to the lack of sunlight. Without a nearby star to provide heat, rogue planets would be left to cool off over time, eventually becoming frozen worlds, their surfaces locked in ice. Despite the frigid conditions, it's possible that rogue planets might not be completely dead and barren. Some scientists speculate that if a rogue planet has a thick atmosphere or an internal heat source, such as radioactive decay or the heat left over from its formation, it could still maintain some warmth beneath its surface. On Earth, we know that life can exist in some of the most extreme environments, from the crushing depths of the ocean to the frozen tundras of the poles. Could something similar happen on a rogue planet, with life eking out an existence deep below the surface, far from the light of a star? One potential scenario involves rogue planets with thick, insulating atmospheres that trap heat and prevent them from freezing entirely. If the planet had enough internal heat, perhaps from the decay of radioactive elements or residual heat from its formation, It could create conditions in which liquid water might exist beneath an icy surface. This brings to mind places in our own solar system, such as Europa, one of Jupiter's moons, which is thought to have an ocean of liquid water beneath its icy crust. On a rogue planet, a similar underground ocean could exist, kept warm by geothermal energy rather than by the heat of a sun. In such an environment, life, if it existed, would likely be very different from anything we know on Earth. Without sunlight to drive photosynthesis, any life forms on a rogue planet would need to rely on other energy sources, perhaps drawing nutrients and energy from the planet's internal heat, as some deep-sea organisms on Earth do near hydrothermal vents. These ecosystems thrive without sunlight, relying on the heat and minerals released by the Earth's interior to sustain life. It's possible that similar ecosystems could exist on rogue planets, hidden deep below the surface in a world of perpetual darkness. Another intriguing possibility is that rogue planets could be home to life forms that have adapted to survive in the harsh conditions of space itself. While this idea may seem far-fetched, there are microorganisms on Earth known as extremophiles that can survive in some of the most inhospitable environments imaginable. These creatures have been found thriving in environments of extreme heat, cold, radiation, and pressure, pushing the boundaries of what we thought was possible for life. If life on Earth can exist in such extreme conditions, might it be possible for life to adapt to the even harsher environments of rogue planets? The discovery of rogue planets has also raised questions about how common these wandering worlds might be. If there are indeed more rogue planets than stars in our galaxy, as some estimates suggest, then the galaxy could be teeming with these cold, dark worlds. Yet despite their abundance, rogue planets are incredibly difficult to detect. Without a star to illuminate them, they remain invisible to most of our instruments, slipping through the darkness of space unnoticed. It's only through indirect methods, such as gravitational microlensing, where the gravity of a rogue planet temporarily bends and magnifies the light of a distant star, that we have been able to detect a few of them. But given how many might be out there, it's likely that we've only scratched the surface of what exists in the dark corners of our galaxy. These rogue planets might also hold clues to the history of our own solar system. If planets can be ejected from their systems and sent drifting into space, it's possible that our solar system once had more planets than it does today. Over billions of years, gravitational interactions between the planets could have flung some of them into the cold depths of space, turning them into rogue planets. Studying rogue planets could help us understand how planetary systems evolve and how they sometimes come apart. The idea of rogue planets also raises profound questions about the nature of planetary systems. We often think of planets as belonging to stars, as part of a solar system, but the existence of so many rogue planets challenges that view. It suggests that planets are not always tied to stars, that some worlds are destined to wander the galaxy alone. What's more, it highlights the dynamic and often violent nature of the universe, where even the most massive objects, like planets, can be cast adrift by the forces of gravity. Boltzmann brains, consciousness born from randomness. Among the many strange and mind-bending ideas that arise when contemplating the vastness of the universe, there is one concept that stands out for its sheer strangeness: the idea of Boltzmann brains. These theoretical self-aware entities are not formed in the usual way, through biological processes or evolution, but instead they could arise spontaneously from the random fluctuations of particles in space. The idea suggests that, given enough time in an infinite universe, a conscious mind could emerge from the chaos of matter and energy, fully formed and self-aware, yet completely alone in the void. The origin of this concept comes from the work of Austrian physicist Ludwig Boltzmann, who, in the late 19th century, explored the nature of entropy and randomness in the universe. Boltzmann theorized that, over long periods of time, random fluctuations could create ordered systems out of chaos just by chance. While Boltzmann was primarily concerned with the physical world, some modern thinkers have taken his ideas and applied them to consciousness itself. Could the same random processes that occasionally bring order to the universe also give rise to a fleeting, self-aware mind A Boltzmann brain? Imagine the vast, empty stretches of the universe, where particles drift aimlessly through space, constantly colliding and separating. In most cases, these particles simply form random, chaotic patterns, but on an incredibly rare occasion, they might spontaneously arrange themselves into something much more complex, something with the ability to think and perceive. A Boltzmann brain would be a fully formed consciousness that arises not through the slow process of evolution, but in an instant born from the random arrangement of particles. This mind would have no history, no body, and no connection to the universe around it. It would simply be a thinking, self-aware entity floating alone in the cold, dark expanse of space. The idea of Boltzmann brains challenges our very understanding of consciousness and existence. For most of human history, we have assumed that consciousness arises from complex biological systems. Brains, bodies, and nervous systems evolved over millions of years. But the Boltzmann brain hypothesis suggests that consciousness could, in theory, arise purely by chance, from the random movements of particles. This raises profound questions about what it means to be conscious. If a mind can emerge spontaneously without a body or an evolutionary past, what does that say about the nature of consciousness itself? One of the most unsettling aspects of the Boltzmann brain idea is the suggestion that, in an infinite universe, Boltzmann brains could be more common than biological minds. The reason for this lies in the sheer scale of the universe. If the universe is infinite, as some theories suggest, then everything that can happen will eventually happen, given enough time. While it's incredibly unlikely for a Boltzmann brain to form at any given moment, in an infinite universe, these rare events would happen an infinite number of times. In fact, they could occur more frequently than the formation of biological organisms, which require specific environmental conditions, resources, and evolutionary processes. This leads to a haunting question. Could we be Boltzmann brains, unaware of our true nature? After all, from the perspective of a Boltzmann brain, there would be no way to tell the difference between a reality that formed through natural evolution and one that came into existence out of randomness. A Boltzmann brain might have memories, thoughts, and experiences that seem perfectly real, even though they are the result of chance. In a sense, the brain would be living in a kind of illusion, unaware that it was created in an instant and that its memories and perceptions have no true history. The Boltzmann brain hypothesis forces us to confront uncomfortable questions about the nature of reality. If consciousness can arise from random fluctuations, how can we be sure that our own reality is stable and consistent? Could our memories and experiences be nothing more than the product of chance, like the fleeting thoughts of a Boltzmann brain? It's an eerie possibility, one that challenges our deepest assumptions about the world around us. Of course, most scientists believe that the Boltzmann brain hypothesis is purely theoretical, and there is no evidence to suggest that we are Boltzmann brains. The idea serves more as a thought experiment, pushing us to consider the limits of our understanding of consciousness and the universe. Still, it highlights just how strange and complex the universe can be. In a cosmos governed by randomness and probability, even the most improbable events, like the spontaneous formation of a conscious mind, become possible. But the concept of Boltzmann brains also touches on deeper philosophical questions about existence and isolation. A Boltzmann brain, if it were to form, would be completely alone in the universe, unlike biological beings, which are part of ecosystems, societies, and civilizations. In the universe, there are vast regions of space where very few galaxies or other forms of matter exist, and they can sometimes stretch for hundreds of millions of light years. The idea that the Eridanus region might be a particularly large void was a logical explanation. After all, if there is less matter in a region of space, light traveling through that area will lose energy, appearing cooler by the time it reaches us. This effect, known as the integrated Sachs-Wolf effect, can create cold spots in the CMB. In the case of the Eridanus supervoid, the idea was that light from the early universe had passed through a giant empty region, losing energy along the way and causing the observed cold spot. But while this explanation seemed plausible, there was a problem. The size of the cold spot was far larger than what would be expected from even a massive void. While voids do exist and can cause slight temperature differences in the CMB, the Eridanus supervoid is so large and the temperature drops so significant that it challenges this explanation. This has led some scientists to wonder if the Eridanus supervoid might not be a void at all, or if it is, whether there might be something even more extraordinary happening within it. One of the more speculative yet intriguing ideas is that the Eridanus supervoid might be evidence of a collision between our universe and another. This theory is rooted in the concept of the multiverse, the idea that our universe is just one of many, each existing in its own bubble of space-time. According to this theory, the universe we live in could have collided with another universe at some point in its distant past, creating a lasting imprint in the fabric of space-time. The Eridanus supervoid, with its strange cold spot, might be the scar left behind from such an interuniversal collision. The idea of a multiverse has been proposed in various forms by cosmologists and physicists, particularly in the context of inflation theory. Inflation refers to the rapid expansion of space that occurred in the first fractions of a second after the Big Bang. Some versions of inflation theory suggest that this expansion could have created not just one universe, but an entire collection of universes, each with its own distinct physical laws and properties. These universes might exist parallel to ours, separated by vast distances in higher dimensional space, but occasionally they could interact with one another. If such a collision did occur between our universe and another, the energy released from that event could have disturbed the smoothness of the CMB, leaving behind anomalies like the Eridanus supervoid. Some researchers speculate that this cold spot could be the cosmic bruise, where our universe and another made contact. In this scenario, the cold spot represents a region of space where the normal structure of the universe was disrupted by the force of the collision, leaving behind a vast, underpopulated void. The possibility that the Eridanus supervoid could be a sign of a multiverse is both fascinating and unsettling. It raises profound questions about the nature of reality itself. If our universe can collide with another, does that mean the boundaries between universes are more fluid than we thought? Could there be other such voids scattered throughout the cosmos, each one a reminder that we are part of a much larger and more complex reality than we ever imagined? Of course, the idea of the multiverse remains speculative, and there is much debate about whether it can ever be proven. For now, the Eridanus supervoid remains an anomaly, an unusually large and cold region of space that continues to defy easy explanation. While the idea of a multiverse collision is compelling, it is not the only possible explanation for the cold spot. Another possibility is that the cold spot is simply an extreme outlier in the normal distribution of temperature fluctuations in the CMB. While the cold spot is unusual, it may not require any exotic explanation. It could be that, in a universe as vast as ours, statistical anomalies like the Eridanus supervoid are bound to occur from time to time. If this is the case, the cold spot might be nothing more than a particularly large and empty void, albeit one that pushes the limits of what we understand about the universe. Despite these competing theories, the mystery of the Eridanus supervoid continues to captivate scientists and astronomers. New observations and simulations may eventually shed light on whether this region of space is a unique anomaly or part of a larger hidden structure in the universe. For now, it stands as one of the most perplexing features of the cosmos, a cold, empty region that beckons us to consider the possibility of realities beyond our own. If the multiverse theory holds any truth, the Eridanus supervoid could be the first real glimpse we have into another universe, an eerie reminder that our universe might not be the only one, but just one bubble in an infinite sea of cosmic possibilities. This idea challenges the very foundations of cosmology, suggesting that the universe we observe may be part of a much larger structure, one that we are only beginning to understand. Whether the cold spot is a sign of a cosmic collision or simply an unusually large void, it forces us to confront the possibility that our universe is not a singular, isolated entity, but part of a broader, more intricate reality. Zombie stars, stars that refuse to die. In stellar evolution, the life cycle of stars often seems predictable. Stars are born, They burn through their fuel, and eventually they die, leaving behind remnants that tell the story of their once brilliant lives. One of the final stages for many stars is the white dwarf phase, where a star, having exhausted its nuclear fuel, collapses into a dense, smoldering core, no longer able to sustain fusion. Yet, even in death, some stars defy expectations. There are stars that, against all odds, seem to come back to life, surviving what should be their final cataclysmic end. These are the zombie stars, white dwarfs that, after experiencing a thermonuclear explosion, manage to survive and linger on as if refusing to die. The phenomenon of zombie stars arises from a rare and fascinating process that occurs in binary star systems, where two stars orbit each other in close proximity. In many of these systems, one of the stars has already reached the end of its life and has collapsed into a white dwarf. Its companion star, however, might still be in an earlier stage of its life, continuing to burn through its hydrogen fuel. Over time, the white dwarf, through its intense gravitational pull, begins to siphon off material from its still-living companion, drawing hydrogen and helium from the outer layers of the nearby star. As the white dwarf accumulates more and more of this material, it grows in mass, inching closer to a critical point known as the Chandrasekhar limit. When a white dwarf approaches this limit, which is roughly 1.4 times the mass of the Sun, the pressure within the star becomes so intense that it can reignite nuclear fusion. This reignition doesn't happen slowly, as it did in the star's original life. Instead, it leads to a thermonuclear explosion, a Type Ia supernova. Type Ia supernovae are some of the most powerful explosions in the universe. They are so bright that they can briefly outshine an entire galaxy, and they are a key tool for astronomers to measure vast cosmic distances. These explosions are thought to be the final moments of a white dwarf, with the intense energy released in the supernova completely obliterating the star. But in some rare cases, something extraordinary happens. The white dwarf survives. Instead of being annihilated by the supernova, it emerges from the explosion as a zombie star, damaged but still intact, refusing to fade into darkness. The survival of these zombie stars is a mystery that challenges our understanding of stellar physics. In a normal Type Ia supernova, the star is consumed by the explosion, with a violent release of energy tearing it apart. But in the case of a zombie star, some part of the white dwarf seems to remain stable enough to withstand the explosion. It's as if the star undergoes a resurrection of sorts, blasted apart, only to reassemble itself in the aftermath. How these stars manage to survive their own thermonuclear explosions remains a topic of intense research. Some scientists speculate that the structure of the white dwarf plays a critical role. It's possible that only the outer layers of the star ignite in the explosion, while the core remains relatively intact. In this scenario, the outer shell is blown away, but the dense, compact core of the white dwarf endures. This could explain how a star might appear to die in a supernova, but then emerge as a faint, smoldering remnant, a true zombie star still clinging to life despite the odds. But what happens to these zombie stars after they survive the explosion? Could they continue to siphon material from their companion star and eventually explode again? Some researchers believe this might be possible. In a few known cases, white dwarfs have been observed surviving multiple explosions, reigniting in a series of smaller, less destructive supernovae. These recurring explosions, known as recurrent novae, suggest that zombie stars could continue to live on, periodically reigniting as they accumulate more material from their companions. One famous example of a possible zombie star is a supernova remnant known as SN 2012Z. In this case, astronomers observed a Type Ia supernova, but instead of the star being destroyed, the white dwarf was still visible after the explosion. This unexpected discovery raised the possibility that some white dwarfs might experience less powerful explosions than others, allowing them to survive the event and continue siphoning material from their companion star over time. These zombie stars could go through multiple supernovae, gradually shedding material with each explosion, but never quite reaching their final demise. The existence of zombie stars forces us to reconsider our understanding of how stars live and die. For much of astrophysical history, the life cycle of a star was thought to follow a clear and linear path: formation, burning, collapse, and death. But zombie stars show us that the universe is far more complex and unpredictable than we often assume. Stars that should have been obliterated in a cataclysmic explosion can somehow survive, continuing to exist in a damaged but still functioning state. It's a reminder that even in the harshest conditions, the universe finds ways to surprise us. Zombie stars also raise intriguing questions about the future of these stellar remnants. If a white dwarf can survive a supernova, what happens to it over time? Does it eventually cool down and fade away? Or could it reignite in another explosion, continuing the cycle? The possibility of multiple explosions suggests that some stars might live far longer than we previously thought, repeatedly coming back to life through the accumulation of material from their companions. These stars also challenge our understanding of supernovae themselves. Type Ia supernovae have long been used as standard candles in astronomy, objects with a known brightness that allow astronomers to measure the distance to faraway galaxies. The idea that some white dwarfs might not be completely destroyed in these explosions raises the possibility that there are variations in the power of Type Ia supernovae that we don't fully understand. This could have implications for how we measure the expansion of the universe and our understanding of dark energy. Zombie stars are a testament to the resilience of the cosmos. Even in the face of overwhelming forces, thermonuclear explosions capable of obliterating an entire star, some remnants manage to persist. One intriguing possibility is that dark matter galaxies, like Dragonfly 44, could help scientists test competing theories of dark matter. There are several ideas about what dark matter could be, ranging from weakly interacting massive particles, WIMPs, to exotic forms of matter that we haven't yet discovered. Observing galaxies like Dragonfly 44 and understanding how dark matter behaves in these environments could help us narrow down the possibilities. Despite its oddities, Dragonfly 44 isn't entirely unique. Since its discovery, astronomers have found other galaxies with similar characteristics, galaxies that are dominated by dark matter and contain very few stars. These galaxies, known as ultra-diffuse galaxies, are spread out over large areas and appear ghostly in optical light. They are difficult to detect, but as technology improves, we are beginning to uncover more of them. These galaxies may represent a new class of objects in the universe, ones that challenge our traditional definitions of what a galaxy is. But why are galaxies like Dragonfly 44 so rare? In most galaxies, dark matter makes up a significant portion of the total mass, but there is still enough visible matter to produce stars, gas, and light. The fact that Dragonfly 44 is almost entirely dark suggests that something unusual happened during its formation, preventing it from becoming a more typical galaxy. Understanding the reasons for this could help scientists refine their models of galaxy formation and provide new insights into the role that dark matter plays in shaping the cosmos. The discovery of Dragonfly 44 has opened up new avenues of exploration in the search for dark matter. It shows us that dark matter isn't just something that exists on the fringes of the universe. It can dominate entire galaxies, shaping their structure and evolution in ways we are only beginning to understand. These dark matter galaxies may be rare, but their existence suggests that the universe is far stranger than we ever imagined. If dark matter can form entire galaxies, it raises the possibility that there are vast regions of the universe that we have yet to detect, filled with galaxies that are almost entirely invisible to us. Hypervelocity stars. When our universe began its rapid expansion from an incredibly hot and dense state, in this context, a white hole might be seen as a kind of initial condition for the universe, an object that existed in a highly compressed state before explosively releasing energy and matter. In this view, the universe itself could be thought of as a result of a massive white hole event, where all the matter and energy that make up the cosmos were expelled outward. But there's another, even more intriguing possibility. Could white holes be connected to black holes in some way? In the strange and often counterintuitive world of general relativity, Some scientists have speculated that black holes and white holes might be linked through a kind of cosmic bridge, more commonly known as a wormhole. Wormholes are hypothetical tunnels through space-time that could, in theory, connect two distant regions of the universe. In this scenario, a black hole might act as one end of the wormhole, pulling in matter, while the white hole acts as the other end, expelling that same matter into a different part of space or even into a different universe altogether. This idea raises the tantalizing possibility that white holes could provide a kind of doorway out of a black hole. If matter were to fall into a black hole, instead of being crushed at the singularity, it could be funneled through a wormhole and ejected from a white hole in another part of space. This concept has been explored in both theoretical physics and science fiction, where wormholes are often depicted as shortcuts through space and time, allowing for faster-than-light travel or even journeys between different universes. However, the existence of such wormholes remains highly speculative. There are significant challenges to the idea of linking black holes and white holes in this way. For one, wormholes are thought to be inherently unstable. The intense gravitational forces involved would likely cause a wormhole to collapse almost instantly, destroying any matter that attempted to pass through it. To keep a wormhole open long enough for matter to travel through would require a form of exotic matter, something with negative energy density, which has never been observed and may not even exist. Despite these challenges, the idea of white holes connected to black holes through wormholes remains an intriguing possibility. If such connections exist, they could provide answers to some of the most profound questions in cosmology, including the fate of matter that falls into a black hole. In the current understanding of black holes, anything that crosses the event horizon is doomed to be crushed at the singularity, lost to the universe forever. But if black holes are connected to white holes, this matter might not be lost at all. It could be ejected into another part of the universe or even another dimension, giving rise to new forms of matter and energy. A different theory that has emerged is that white holes could exist as time-reverse versions of black holes. In this scenario, while black holes represent the forward progression of time, where matter falls in and is trapped, white holes would represent the reverse. In this time-reversed universe, matter would be pushed out instead of pulled in. This raises fascinating questions about the nature of time itself and whether it might be possible for white holes to exist in regions of the universe where time behaves differently. Some physicists have even suggested that the mysterious objects known as gamma-ray bursts could be related to white holes. Gamma-ray bursts are incredibly powerful flashes of high-energy radiation, believed to be caused by the collapse of massive stars or the merging of neutron stars. However, their extreme energy output has led some to speculate that they might be connected to white holes, perhaps representing the moment when matter is violently expelled from a white hole, releasing massive amounts of energy in the process. This idea remains speculative, but it highlights the creative ways in which white holes have been incorporated into modern astrophysical thinking. The mystery of white holes challenges our understanding of the universe on a fundamental level. While black holes are a well-established part of astrophysical theory, white holes remain elusive, existing only in the theoretical realm. If they do exist, they could provide answers to some of the most perplexing questions in modern physics, from the nature of time and space to the ultimate fate of matter in the universe. They also push the boundaries of what we think is possible in the cosmos, offering a glimpse into a reality where the rules we take for granted, such as the one-way nature of time and the irreversible destruction caused by black holes, might not be as rigid as we believe. For now, white holes remain an enigma, a concept born from the same equations that gave us black holes, but still waiting to be confirmed or disproven. As our understanding of the universe continues to evolve, and as new observations and experiments probe the farthest reaches of space and time, we may one day find evidence that white holes are not just theoretical constructs, but real objects with profound implications for our understanding of the cosmos. Until then, the idea of white holes invites us to keep questioning, to explore the edges of what we know, and to imagine a universe far stranger and more complex than we can currently comprehend. a universe where black holes and white holes might be two sides of the same coin, linked by the invisible threads of space-time, creating pathways between distant regions of space or even alternate realities. The death of a black hole. Black holes are often seen as the ultimate endpoints in the life cycle of massive stars. When a star exhausts its nuclear fuel and can no longer support itself against the force of gravity, it collapses, forming a black hole, an object so dense that not even light can escape its grasp. For decades, the conventional view has been that black holes contain singularities at their cores, points of infinite density where the known laws of physics break down. But in recent years, a new and intriguing idea has emerged, one that challenges the notion of singularities and offers a different vision of what might happen inside a black hole. This concept centers around the idea of Planck stars, theoretical objects that could form inside black holes. When they reach a certain size, instead of collapsing into a singularity, these stars might bounce back, releasing their energy in a process that could illuminate the mysteries of quantum gravity. The idea of Planck stars comes from the intersection of two major fields in physics: general relativity, which describes gravity and the structure of space-time, and quantum mechanics, which governs the behavior of particles at the smallest scales. Normally, these two theories don't work well together. General relativity predicts singularities inside black holes, but quantum mechanics suggests that such infinite densities are impossible. The concept of a Planck star attempts to reconcile these two perspectives by introducing quantum gravity into the heart of a black hole. At the core of this idea is the Planck scale, a set of physical limits where quantum effects become significant for gravitational systems. When a black hole shrinks to a size comparable to the Planck length, an incredibly small distance of about 1.6 times 10 to the power of negative 35 m, quantum effects are expected to become dominant. At this point, gravity would no longer behave as it does in classical physics. Instead of continuing to collapse into a singularity, the black hole might reach a minimum size and then undergo a quantum bounce. This bounce would prevent the formation of a true singularity and could release the energy stored in the black hole in a way that avoids the paradoxes of infinite density. The term Planck star refers to the object that forms during this quantum bounce. Rather than becoming an infinitely dense point, the collapsing matter inside the black hole reaches the Planck scale, where quantum gravity takes over. The extreme pressures and densities at the scale create a repulsive force that counteracts the gravitational collapse, causing the black hole to stop shrinking and begin to expand outward again. This expansion would release the energy stored in the black hole over an incredibly long time scale, allowing the black hole to slowly die in a way that is different from the traditional view of black hole evaporation. One of the most famous ideas about the death of black holes is Hawking radiation, proposed by physicist Stephen Hawking in 1974. According to this theory, black holes are not entirely black. They emit tiny amounts of radiation due to quantum effects near the event horizon. Over incredibly long periods, this radiation causes black holes to lose mass and energy, eventually leading to their complete evaporation. But Hawking radiation is an extremely slow process, especially for large black holes, which can take longer than the current age of the universe to fully evaporate. Planck stars offer an alternative to the slow evaporation process. In this scenario, instead of gradually radiating away energy, a black hole could release its energy all at once in a dramatic event when it reaches the Planck scale. This would create a brief but intense burst of energy as the black hole undergoes its quantum bounce, effectively exploding and dispersing its remaining mass. Such a process would happen much more quickly than Hawking radiation, potentially allowing black holes to disappear in a finite amount of time rather than lingering for eons. The possibility of Planck stars forming inside black holes also raises intriguing questions about the nature of space and time inside a black hole. Time itself behaves differently from what we experience outside. As matter falls into a black hole, time appears to slow down, eventually seeming to stop altogether at the event horizon. If a Planck star forms at the heart of a black hole, it could be that time as we understand it, no longer applies in the same way. The quantum bounce could represent a kind of reset for space-time, where the normal rules of physics break down and are replaced by new quantum laws. This raises a profound question. Could the formation of a Planck star represent a kind of rebirth for the black hole? If black holes don't end in singularities but instead undergo quantum bounces, it might mean that black holes aren't the end of the story but a transition to something else. In this view, black holes could be seen as temporary phases in the life cycle of matter, with the potential to release their energy back into the universe, rather than trapping it forever. The energy released during the quantum bounce could even contribute to the formation of new structures in the universe, such as stars or galaxies, providing a link between the death of one cosmic object and the birth of another. Another important aspect of the Planck star hypothesis is what it can teach us about quantum gravity. Quantum gravity is a long-sought theory that would unite general relativity and quantum mechanics into a single framework, allowing us to understand how gravity works at the smallest scales. Black holes are one of the best places to study this because they represent environments where both quantum effects and gravity are incredibly strong. If Planck stars exist, they could provide a natural laboratory for testing theories of quantum gravity, giving physicists a way to explore the deepest mysteries of the universe, from the nature of space-time to the behavior of matter at its most fundamental levels. One of the challenges with the Planck star idea is how to detect such objects. Since the process would occur deep inside a black hole, behind the event horizon, it would be impossible to observe directly. However, there might be indirect ways to detect the effects of a Planck star's quantum bounce. For instance, if a black hole were to undergo this process, it could release a burst of radiation or particles that could be observed from a distance. These signals would be different from the typical emissions we associate with black holes, offering clues that a quantum bounce had taken place. In addition, the energy released during the quantum bounce could have observable effects on the surrounding environment. If a black hole were located near a star or a planet, the sudden release of energy from a Planck star could disrupt nearby matter, creating shock waves or jets of particles that could be detected by telescopes. These observations could provide valuable evidence for the existence of Planck stars and offer a new way to study the end stages of black holes. The idea of Planck stars also has implications for the information paradox, a long-standing problem in black hole physics. According to classical general relativity, anything that falls into a black hole is lost forever, including all the information about the matter that fell in. But in quantum mechanics, information can never be truly lost. This creates a paradox. If black holes contain singularities where information is destroyed, it would violate the principles of quantum theory. Planck stars might offer a solution to this problem by preventing the formation of singularities. Planck stars could allow the information stored in a black hole to be released during the quantum bounce, preserving the laws of quantum mechanics and resolving the paradox. The expanding universe and the fate of everything. The universe as we know it is not a static entity. It is constantly expanding, a discovery that has revolutionized our understanding of cosmology. When astronomer Edwin Hubble first observed in 1929 that galaxies were moving away from each other, it became clear that the universe itself was growing, stretching outward in all directions. For decades, this expansion was thought to be slowing down due to the gravitational pull of matter within the universe. The gravitational pull that holds stars in orbit around the center of a galaxy would fail, causing stars to scatter into the vastness of space. But the process wouldn't stop there. As the universe's expansion continues to accelerate, even the solar systems that make up galaxies would be pulled apart. Planets would be ripped from their orbits around their stars, and moons would be torn away from their planets. Eventually, stars themselves would no longer be able to hold together, as the force of dark energy would overwhelm the nuclear forces that keep them intact. Stars would explode into clouds of gas and dust, their remnants scattered across an ever-growing universe. In the final stages of the Big Rip, the expansion would accelerate to such an extreme that it would begin to affect the atomic scale. The forces that bind atoms together, the electromagnetic forces between electrons and nuclei, would weaken, causing atoms to break apart. Molecules would disintegrate, and even the most fundamental particles, such as protons and neutrons, would be torn apart by the unstoppable expansion of space. At this point, the universe would be a vast, empty expanse devoid of any structure, with nothing left but a thin soup of subatomic particles spread across an infinitely expanding void. This grim scenario paints a picture of a universe that is not just expanding, but unraveling. The forces that hold everything together, gravity, electromagnetism, the strong nuclear force, would all be overcome by the relentless push of dark energy. The Big Rip is a cosmic endgame where everything is torn apart, leaving behind only the cold emptiness of space, expanding forever without end. While the Big Rip is a compelling and terrifying theory, it is by no means the only possible fate for the universe. There are other competing ideas, such as the heat death, in which the universe continues to expand but gradually cools as stars burn out and galaxies drift farther apart. In this scenario, the universe would reach a state of maximum entropy, with all energy evenly distributed and no structure remaining, an endless cold darkness where nothing can happen because there is no available energy. Another possibility is the Big Crunch, where the expansion of the universe reverses and everything collapses back in on itself, potentially leading to a new Big Bang and the birth of a new universe. Yet the Big Rip stands out because of the sheer finality and violence of the process. Unlike the heat death, where the universe slowly fades away, or the Big Crunch, where everything is pulled back into a singularity, the Big Rip suggests a cataclysmic end where everything is torn apart, leaving no possibility of recovery or rebirth. The idea that the universe could end in such a way challenges our understanding of existence and the nature of reality itself. For much of human history, the universe was seen as eternal and unchanging. The stars in the night sky seemed to move in predictable patterns, giving the impression of a stable and permanent cosmos. But the discovery of the expanding universe shattered that illusion, revealing that the universe is dynamic, always changing, and subject to forces that we are only beginning to understand. Knowing that the universe is expanding at an accelerating rate, driven by a mysterious force we call dark energy, forces us to confront the possibility that everything we know, our planet, our solar system, our galaxy, and even the fundamental particles that make up matter, could one day be torn apart. It's a humbling thought, one that puts our existence into a cosmic perspective. The forces that govern the universe operate on scales of time and space that are almost impossible for the human mind to comprehend. While the timeline for the Big Rip, if it were to occur, is so vast that it stretches far beyond the lifespan of humanity, it raises deep philosophical questions about the nature of the universe and our place within it. Can we truly grasp the scale of such an event? The distances involved in the expansion of the universe are beyond anything we experience in our daily lives, and the forces at play are so powerful that they challenge the limits of human imagination. Yet, as we explore the universe, we continue to learn more about its nature and its ultimate fate. The idea of the Big Rip is a reminder that the universe is not static or permanent. It is a dynamic, evolving entity, and we are a small part of its unfolding story. In the face of such vast cosmic forces, one might wonder what, if anything, could survive. Would any trace of the universe's early history remain after the Big Rip, or would all information be lost as matter is torn apart and scattered across an infinitely expanding void? These are questions that physicists continue to explore using the tools of cosmology and quantum mechanics to probe the deepest mysteries of the universe. Ultimately, the fate of the universe, whether it ends in a Big Rip, a heat death, or some other scenario, is a question that touches on both science and philosophy. It forces us to confront the transience of everything we know and the vast, impersonal forces that shape the cosmos. The expansion of the universe and the possible end it suggests serve as a powerful reminder of the scale and complexity of the universe, one that continues to expand and evolve, with or without us. Rogue black holes. In the vast expanse of the cosmos, where galaxies swirl and stars are born and die, there exists a more elusive and enigmatic class of objects, rogue black holes. Unlike the familiar black holes that anchor themselves in the hearts of galaxies or form in the remnants of massive stars, rogue black holes wander through space, unbound by any gravitational ties to a galaxy or star system. These solitary giants drift through the universe, their presence felt only through their gravitational effects and the occasional interaction with other cosmic entities. The concept of a rogue black hole challenges our traditional view of these mysterious objects. Black holes are typically associated with dense, energetic environments, places where matter is compressed to extreme densities. Most are found at the centers of galaxies, where they grow by accreting surrounding matter or merging with other black holes. However, the idea of black holes moving through the intergalactic void, far from the influence of any galaxy, opens up new possibilities for understanding their formation, behavior, and impact on the universe. The formation of rogue black holes is a topic of ongoing research. One possible scenario involves the ejection of a black hole from its original galaxy. This could occur through a variety of mechanisms. For example, if a black hole were part of a binary system, a pair of black holes orbiting each other, an interaction with another massive object could provide enough gravitational force to slingshot one of the black holes out of the galaxy. Another possibility is the result of a black hole merger. When two black holes collide and merge, the newly formed black hole could be given a significant kick, propelling it out of its host galaxy and into the depths of intergalactic space. Additionally, black holes might form in isolation within the dense environments of star clusters or the early universe. These primordial black holes, formed shortly after the Big Bang, could be scattered throughout the cosmos, drifting freely if they were not captured by any galaxy or star system. Such black holes would have been formed from the collapse of high-density regions in the early universe, predating the formation of galaxies and their associated structures. Despite their solitary nature, rogue black holes are not entirely isolated from the rest of the universe. Their gravitational influence extends far beyond their immediate vicinity, affecting nearby stars and gas clouds. As rogue black holes travel through space, they can disrupt the paths of stars and gas clouds they encounter, potentially causing them to change their trajectories or be pulled into the black hole's grasp. These interactions could create observable phenomena, such as high-energy radiation from the accretion of matter. Even if the black hole is not part of a galaxy, the existence of rogue black holes also poses intriguing questions about their potential impact on the structure and dynamics of the universe. If rogue black holes are numerous and spread throughout intergalactic space, they could contribute to the overall mass and gravitational effects observed in the universe. Their presence might affect the distribution of dark matter, a mysterious substance that interacts only through gravity and is thought to make up a significant portion of the universe's mass. In terms of observational evidence, detecting rogue black holes presents a significant challenge. Unlike black holes within galaxies, which can be observed through the radiation emitted by material falling into them, rogue black holes do not have the same easy-to-detect signatures. However, astronomers are developing innovative methods to find these elusive objects. One approach involves looking for gravitational lensing, where the gravitational field of a black hole bends the light from objects behind it, creating observable distortions. Another method is to search for the effects of rogue black holes on the movement of stars and gas clouds in their vicinity. Advanced telescopes and detection techniques continue to improve, increasing the likelihood of finding evidence of these cosmic wanderers. The study of rogue black holes also raises broader questions about the nature of black holes and their role in the cosmos. Their presence suggests that black holes are not merely passive remnants of stellar evolution, but dynamic entities capable of interacting with and influencing their surroundings in profound ways. The behavior of rogue black holes might offer insights into the formation and evolution of black holes in different environments, including the early universe. Furthermore, the existence of rogue black holes could have implications for our understanding of cosmic collisions and interactions. If rogue black holes are numerous and capable of traveling through intergalactic space, they could potentially collide with other black holes or even encounter other objects, such as neutron stars or planets. These interactions could lead to significant cosmic events, such as gravitational waves or high-energy bursts, which could be detected by astronomers and provide valuable information about the properties and behavior of black holes. The Sagittarius A paradox. At the heart of our galaxy lies Sagittarius A*, a supermassive black hole of extraordinary mass and power. Yet, despite its immense gravitational pull and the countless phenomena observed around it, Sagittarius A* presents a curious paradox. It appears relatively calm compared to other supermassive black holes scattered throughout the cosmos. This calm demeanor has puzzled astronomers and physicists, who seek to understand why such a massive black hole is not exhibiting the intense activity seen in its counterparts. Sagittarius A* is situated approximately 26,000 light-years from Earth, nestled within the dense and bustling core of the Milky Way galaxy. This black hole is estimated to have a mass of about 4 million times that of our Sun. By comparison, many other supermassive black holes in the universe, especially those in the centers of active galaxies, are known for their spectacular displays of energy and matter. These active galactic nuclei often emit powerful jets of radiation and high-energy particles, and their accretion disks shine brightly across the electromagnetic spectrum. In contrast, Sagittarius A* appears relatively subdued, emitting only faint X-rays and radio waves, and lacking the pronounced jets observed in more active black holes. The subdued activity of Sagittarius A* has led to several intriguing questions about its nature and behavior. One aspect of this paradox is the rate at which Sagittarius A* is feeding on surrounding matter. Typically, supermassive black holes grow by accreting gas, dust, and other material from their surroundings. As this material spirals inward, it forms an accretion disk, heating up to extreme temperatures and emitting intense radiation. However, Sagittarius A* seems to be consuming material at a much slower rate compared to other supermassive black holes. This lower accretion rate might explain its relative calmness, but it raises further questions about why this particular black hole is not as active as expected. Another factor contributing to the paradox is the historical activity of Sagittarius A*. Observations suggest that this black hole might have been more active in the past. Evidence from astronomical surveys indicates that the Milky Way's core has undergone periods of intense star formation and high-energy activity. It is possible that Sagittarius A* was once a more vigorous source of radiation and energy, with activity levels comparable to those of other supermassive black holes. Over time, however, it might have entered a quieter phase, possibly due to a decrease in the availability of accreting material or changes in its surrounding environment. The presence of a dense stellar environment around Sagittarius A* also adds to the complexity of the situation. The region surrounding this black hole is filled with a large number of stars and gas clouds, which could influence its behavior. For instance, interactions with nearby stars might affect the flow of material into the black hole, altering its accretion dynamics. Additionally, gravitational interactions and tidal forces from the surrounding stellar population could impact the rate at which matter is drawn into the black hole. The relative calmness of Sagittarius A* may also be influenced by the nature of the material it is accreting. The gas and dust surrounding Sagittarius A* might be less dense or cooler compared to the more active regions around other supermassive black holes. This could result in a lower accretion rate and reduced radiation output. Furthermore, the magnetic fields and other physical conditions around Sagittarius A* might differ from those in more active black holes, affecting its overall behavior and energy output. Another intriguing possibility is the role of feedback mechanisms in regulating the activity of Sagittarius A*. Supermassive black holes can influence their surroundings through powerful outflows and jets, which can impact the rate of accretion and the overall activity of the black hole. These feedback mechanisms might have played a role in shaping the current state of Sagittarius A*. If the black hole underwent periods of intense activity in the past, it might have expelled significant amounts of material and energy, leading to a reduction in its accretion rate and a more subdued state in recent times. Understanding the Sagittarius A* paradox requires a comprehensive approach, combining observations, theoretical models, and simulations. Researchers use a variety of techniques to study this black hole, including radio telescopes, X-ray observatories, and computer simulations. By analyzing the data collected from these observations, scientists can gain insights into the behavior of Sagittarius A*, its accretion processes, and its interactions with the surrounding environment. Recent advancements in observational technology and computational methods are providing new opportunities to investigate the Sagittarius A* paradox. For instance, the Event Horizon Telescope, which captured the first image of a black hole in the galaxy M87, is also working to observe Sagittarius A*. This collaboration aims to provide more detailed images and data on the black hole's event horizon and surrounding region, which could help resolve some of the outstanding questions about its behavior. In addition to direct observations, theoretical models play a crucial role in understanding the dynamics of Sagittarius A*. Researchers use simulations to explore various scenarios, such as different accretion rates, material densities, and feedback mechanisms. These models help to test hypotheses about the black hole's past activity, its current state, and the factors contributing to its relative calmness. The Sagittarius A* paradox not only challenges our understanding of supermassive black holes, but also provides valuable insights into the broader context of galaxy formation and evolution. The behavior of Sagittarius A* could have implications for the study of other galaxies and their central black holes, helping to refine our models of galaxy dynamics and black hole growth. Additionally, the insights gained from studying this black hole might inform our understanding of the Milky Way's history and its role within the cosmic landscape. In essence, the calm demeanor of Sagittarius A* serves as a reminder of the complexity and diversity of the universe. It highlights the fact that, even within the realm of supermassive black holes, there are variations in behavior and activity that defy simple explanations. As researchers continue to explore this enigmatic object, they are not only seeking to resolve the paradox, but also to deepen our understanding of the fundamental processes that govern the universe. The study of Sagittarius A* exemplifies the ongoing quest to unravel the mysteries of the cosmos. By investigating the nuances of its behavior, scientists are piecing together the intricate puzzle of black hole dynamics and galaxy evolution. The journey to understand why Sagittarius A* appears relatively calm is a testament to the curiosity and perseverance that drives scientific exploration, shedding light on the hidden complexities of the universe and our place within it. I hope you enjoyed the video. Feel free to subscribe to the channel if you did.